So we understood what is Habiroff algebra. Yeah, so it's just a braided Hopf algebra object in some category with all the structure morphisms satisfying these relations. Yeah, so we a priori we don't know what it is, but let us just try to study this object. So I think I can answer. No, I think I will comment later about the Riemann structure. So what I would like now to introduce, it's a category. I'll call this 3-alg. So, and this will be a braided monoidal category, freely generated by the Habiroff algebra. So this is my abbreviation for Habiroff. Then there were conjecture stated already, which I like to call Kerla or Habiroff-Kerla conjecture, whatever you, or I'm not very sure I'm politically correct, because Kerla is actually stated this conjecture, and this is a conjecture that there exists. So the category of 3-cob is equivalent to 3-alg. So this is just a braided monoidal category freely generated by this object, by braided Hopf algebra object with these additional axioms. And so the conjecture is this is exactly the 3-cob. So there is an equivalence of these two categories. Okay. And the story about this conjecture is that actually, so Kerla was working in the 90s, so till 2000, 2005, perhaps he was working on algebra. So it's actually his word, algebraization of low-dimensional topology. So he wanted to have an algebraic category completely describing three-dimensional cobordism. And so he postulated some set of axioms, but his axioms were not this one. So it was few lacking. So I think this main one about this is a joint action. No, this one it was there. Sorry, I cannot tell now which exactly was lacking, but his set of axioms was incomplete. And then actually, so Habiroff never wrote anything about this, but he inspired Asaida. So Marta Asaida wrote a paper where she stated all this axiom exactly in the way I stated it here. And the paper appeared, I think, in Journal of Knot Theory around 2011 or 2012, something like this. And she claimed there that this hold and that the Habiroff will publish the proof. And the proof has never appeared till now. So therefore, I don't know. So I don't know whether, so I mean, perhaps he will be not happy with my name here, but I'm still, so I would like to honor his contribution. So I would like to put his name, but perhaps he's unhappy because he would, so, but anyway, so I don't know whether he proved, I don't know how he proved his works and so on. And what we actually prove is, and this is our recent result with all people I mentioned there, so it's Bobtcheva, De Renzi, and Piergallini, and we prove actually that there exists, so the functor pi, which sends 3-alg to 3-cob, is an equivalence of categories, of braided monoidal category. Okay, so the conjecture is true. The proof is not, so actually, so the proof which I will present to you goes through the 4-dimensional topology. So actually, and now I'm explaining so how the rest of the lectures will be organized. So what we will actually state, but probably, okay, so before I'll do this, let me first state some consequences of this theorem. So this means that this algebraic category actually knows everything about topology. So this means, for example, that if you have three-dimensional cobordism going from the genus G surface, for example, to itself. And you know that the inverse of this functor, which exists because this is the inverse, which goes from 3-cop, which we actually will construct explicitly. So this functor is known explicitly. And if we know that image of this is just identity of this object, then you know that your cobordism is actually just the surface times an integral. Yeah. So this category, just if you know that the corresponding algebra object is something else, then you know what is a cobordism is exactly. So I mean, it's so usually in topology, people are extremely happy about such kind of results because you can really detect every cobordism by this. Then this result also classify all three-dimensional TQFTs on 3-cop. So it has so this universal property that tells you that if you have any category C and you would like to know whether there exists a functor from 3-cop to this category, that actually to define such a functor, the only thing you need to do is to take this Habiru algebra object, which generates 3-cop, and to find an image for, and this image should be a Habiru algebra object in this category. So this is how any TQFT can be constructed. And so A is a Habiru algebra object in C. Okay, and then so let me also cite our theorem, which is already published. So this is not yet published, but we are writing this paper, so all is proven. So we hope in a few months it will be online. Yeah.
How do you call the associators this model and functor? Because the algebra itself doesn't see that, and maybe there is some, I don't know, there is some non-trivial associators in C. So
if I can find, so what I'm claiming, if I have any braided monoidal category, and if I can find HHO inside, then there exists a TQFT like this. That's all what I'm claiming. Yeah, and this is just straightforward because this is according to this theorem is 3-alk. 3-alk is freely generated. So the only to define a functor, you just need to send generator to generator, that's it, and check the relation, and the relation is satisfied because this is required. So this is almost the topological classification of all 3D TQFTs. No, I'm not saying anything about unique. So perhaps this in C. This is unique, yeah, absolutely. This is unique, exactly. But perhaps this C may have different. So this I don't know. Yeah. But any, so what I'm saying, any TQFT, guys, is defined by saying exists H just for to Habiru algebra object. Okay, and then to show you that such algebras exist, this is what I was claiming before the before the break. So let us assume that my category C be a finite unimodular factorizable Riemann category. Then there exists a braided monoidal functor, which I'll call G3, which sends 3-cop to C. And now the generating object, yeah, exactly. So the equivalence between 3-alk sends F1 to H. So therefore, I'm sometimes identifying them already. Yeah, but actually one should. So the generating object 3, I call this F1. Yeah, this is one punctured surface with one handle. So this F1 is sent to the end, which exists because of the finiteness. This is the result. So it's always, you can always construct this three-dimensional TQFT for any finite or unimodular factorizable Riemann category. Okay, And in the case, so the main source of the example is clearly given by the quantum groups. So if your category is H mod, where H is a finite dimensional unimodular of Hopf algebra, for example, quantum group, factorizable Hopf algebra, the end, you can even identify, so you can end in H mod, it's just the adjoint representation. So you can just identify this. So you can, so this is the end. And so this adjoint representation, it's just as a vector space, it's H itself. And the action is the adjoint action, where H adjoint acting at X is defined as H1, X S of H2, where I'm using the Swidler notation for the co-multiplication of H. Yeah, so you see, so you have infinitely many examples of these Haber-Hopf algebras, where the generating object is just the end of such a category or just the adjoint representation of any quantum group. So this is what I wanted to say about just.
So I do not understand the three algebras. So is it generated by a single Haber algebra, or you collect all Haber algebras and?
No, just by one. So if just you have just one object with this satisfying this relation, then you consider a category freely generated by this one object.
Oh.
Yeah, it's a braided monoidal category freely generated by this one object. This is 3-alg. So this is kind of a universal three-dimensional cobordism category.
So this is not algebra, but just object or algebra. I'm confusing.
Yeah, so probably, yeah. So braided Hopf algebra. Yeah.
It is a Hopf algebra.
Yeah, it's a Hopf algebra. Yeah.
Okay. So three algebra, it depends on choice of your Hopf algebra.
Yeah, sure. So I mean, this is.
Is it unique? Not unique. Haber-Hopf algebra is not unique. Am I right?
Sorry, I don't understand what this. So I mean, this is the definition.
Definition, yes, but.
So there maybe, so for example, so if you give me any quantum group, for any quantum group, the adjoint representation is a Haber, so satisfy all this is a Haber-Hopf algebra object.
So just in this case, three algebra is depending on the choice of your Haber-Hopf algebra, am I right?
No. This is a universal. This is a universal category generated by just one object. So, for example, in quantum group, you can have other relation as well.
So okay, so three algebra is category generated by single object. That's what you mean.
Yep.
Okay.
Exactly. Yeah, exactly. This is just a category. So that's it straight. So let me now come to the of this Haber-Keller conjecture, or of the theorem I just mentioned. Yeah, so of this theorem here. And so it's very surprisingly, the proof of the theorem, and this is for the moment, it's the only existing proof, goes through four-dimensional topology. And actually, it's produced a much more interesting result than this one. So namely something similar for some four-dimensional topological category here and category which is 4-alg here. So basically what we will prove, this theorem will follow from what I will call main theorem. And this main theorem was actually proven by Bobtcheva and Piergallini in 2012, I think. And this is a single issue of the journal, which is about 230 pages. And basically, so when we used their paper to prove our theorem there, the referee told us that this is completely impossible to understand what is written there. So and this was never cited before, and so on, and so somehow so this work, so it's amazing work, but it's kind of was not really mentioned by the people. And so therefore, and also, so I mean, one of the reasons, according to our referee, is that it uses complicated techniques from topology, like branch covering, and complicated technique from the algebra, and there is no community which understands both of them. And so therefore we decided to solve this problem by writing another paper. So what we are writing now, and I hope it will be really in a few months available. So this is our paper with Marco De Renzi and also Bobtcheva and Piergallini, and I hope it will be in 2023 soon appeared. And this is a proof which doesn't use, so which is much more straightforward. And so it's a proof of the following results. So there exists some category of so-called four-dimensional two-handed bodies. I will define it. So this will be a main, so like probably all today I will define it. This is some topological categories. This is which one dimension higher than 3-cob. So it's a four-dimensional handled bodies. And there exists some algebraic category, which is called 4-alg, which is generated, so it's defined in the same way. So it's a braided monoidal category generated by some Hopf algebra object with some relations. And what they prove at that time is the equivalence between these two. But what actually then, so the theorem over there follows by taking boundary of this four-dimensional two-handled body. And what you obtain is a three-dimensional cobordism. And actually, so this is just really, this is taking boundary, and this is just surjective map there. And you have also surjective map from this 4-alg into 3-alg, which is basically you just add two more relations. So this is more general. So basically, to construct presentation of this one, you can also take H mod for some quantum group, but you should definitely remove factorizable. So this is the idea. So it should not be factorizable, otherwise it just belongs to 3-alg. So and it doesn't see the four-dimensional topology and see only three-dimensional topology. And basically this equivalence will produce you this equivalence which I just mentioned there. So this is the structure. So this is how we will prove. So basically I will comment mainly on this main theorem. So how the four-dimensional handled bodies can be described by some algebraic category. Okay, and again, so here you so from this main theorem you will also have all the result which we also proved with Marco before, like for example, so given a finite unimodular, so forget about factorizable ribbon category, there exists a braided monoidal functor, which we will call G4, which will go from this four-dimensional category, and which will sell. So here the object will be S2. The object will be S1 times D2, and it will send to the end, and so on. And the result will be that if, exactly, let me write it here. So if this category C is factorizable, so this means the Hopf pairing is invertible, then in this case, this functor G4 factorizes through this boundary functor and G3. So this means that, so probably many of you were working on so-called modular categories, which are by definition factorizable. And so this is the reason, and many people were since to arrive in the 90s, they were working on upgrading the like Rishlehin-Turaev invariants, for example, to the four-dimensional manifold, and it's never worked because they usually were using this factorizable stuff. So they were all starting with a factorizable category, And so, and the result, so after they define, so for example, they were using 6J symbols or spines or whatever to define four-dimensional manifold, or shadows, for example, Turaev was using. And after they constructed the invariant, the result was always they just see the boundary of this of this four-dimensional manifold. And this is exactly what happens here. So in the case when you have a factorizable category, then your factor, which a priori could be interesting, it just factorizes through the boundary and doesn't see any four-dimensional structure. So therefore, so basically, so the aim and the reason why I'm giving this lecture is just to motivate you to look at the unimodular ribbon categories which are not factorizable. So because this category may see much more, they may see this four-dimensional topology, which is actually a very interesting feature. Okay, and so now let me use finite. It's just finitely many. So for the algebra, so basically so for H mod, this means just H is finite dimensional.
I seem to recall from Harshit's talk yesterday, so that the unimodular, if you're saying unimodular, then you're generally not talking about something that is semi-simple. If that's
exactly. So in this business, exactly. So if you would like to have something interesting, so it should be non-semisimple and not factorizable. And unimodular means it's exactly that's.
Excuse me. So that is the definition of factorizability, am I right?
No, this is a consequences of this is a consequence. So the definition of factorizability, it's you have a Hopf pairing which is non-degenerate, or you have monodromy, so you have braiding, yeah, and from braiding you can construct monodromy matrix, yeah, which is double braiding, and this matrix is invertible. This is factorizable.
What if you have incrementally simple? What if you have incrementally simple object?
So this is so the problem. The problem with this construction, with this theorem, if you have infinitely many objects, then you don't know whether such an end exists. So the only condition why I put this finite, it's for me, it just guarantees the existence of the end.
I guess I do have a follow-up question, which I think is probably somewhat related to Jin Chung's question, which is since you're not generally semi-simple here, so if you have factorizable invertibility of the Hopf which is what I'm used to it being indexed like the index by the simple objects, but you're not semi-simple here, so I'm a little bit.
No, but it's okay. So I don't want to. So basically, for me, the factorizability. So basically, if this equation holds, then it's factorizable. So that's it. So I have a Hopf pairing, and I have Hopf copairing, and they compose to. So this means there is no kernel. That's it. So forget about matrices. So sorry, it was okay. So I'm jumping too quickly from one side to the other.
We know some non-semisimple.
So, for example, SL2 at the fourth root of unity. At the root of unity of order 0 mod 4. It's non-semisimple, it's non-factorizable, and we wrote a paper with Marco about this case. So I will postpone this to the next lecture. Okay. So for the moment, so my idea was now is to convince you that the four-dimensional topology is even more interesting than the three-dimensional one. Already three-dimensional one is fascinating, yeah, but the four-dimensional one is even more, yeah. And so let us go to the 4D topology. So I know you're not topologist, but still you may know that in dimension 4, so this is the first dimension where it happens that the smooth category of four-dimensional manifolds and the top category of topological four-dimensional manifolds are not equivalent. So like it was for like n-cob for n equal 1 to 3, it doesn't matter which structure you put on your, so piecewise linear or simplicial or smooth or differentiable or topological, it's all the same, they're all equivalent. Starting from dimension 4, so the worlds start to be much more complicated. So, and people don't know much in general. So for example, it's even unknown. So what is pi 0 of the group of the diffeomorphism of R4? So it's even unknown how many components this group of diffeomorphisms, like for example, mapping class group diffeomorphism of surfaces. This is something which people know. Yeah. So in R4, it's a complete mystery, and R4 itself has uncountably many different smooth structures. Okay, so this is already one feature which shows you that this is so like to study smooth category may be very complicated. Then the smooth, like 4D smooth Poincare conjecture is still open, and this is the only case which is still open. Yeah. So there are all other dimensions; they are all proven. It's only 4D, which is which makes problem here. And perhaps let me also cite Markov's theorem from 58, saying that there is no algorithm that can tell apart two arbitrary closed four-dimensional manifolds. Can tell whether arbitrary closed four manifolds are diffeomorphic. So you see, it's a complicated subject to study, but still one should not be discouraged. So there are still many results in smooth and also in topological case concerning just four-dimensional manifold with given pi 1. So for example, semi-simple four-dimensional manifolds. So basically the general classification, you can forget about it, but manifold with given pi 1, for example, you can hope to understand. And the main tool to study four-dimensional manifolds are so-called handle decompositions. So this is a generalization of Hilgard splitting for a three-dimensional case. So let me speak about handle decompositions. So an n-dimensional K handle, which I'll denote by HKN, it's just dk times dn minus k, where this is a k-dimensional disk. Yeah, so you can think about this as a thickening of a K cell. Yeah, so it's n-dimensional thickening of a k-dimensional cell. And given any four-dimensional manifold X with a boundary, you can construct out, so X will be a four-dimensional manifold. You can construct a new one by adding a handle, say k-dimensional n handles. So yeah, okay, if it's n-dimensional manifolds, then you can add an n-dimensional K handle. And you can, so you add it by gluing this handle along the boundary. So this is a called attaching map to the boundary of X. So this is attaching map. And so in general, the picture looks like this. So you have your X. So you delete from the boundary of X. So this is so-called attaching spheres. So these are attaching spheres. This is exactly this. So attaching sphere. So these two guys are attaching sphere for the one handle. This is the core of the handle. And this is the belt sphere. So the belt sphere of the handle. This is the second part of the boundary. This is dk. But if I put this d on the other sides, and I'll get belt sphere. And in general, so the handle body decomposition for any manifold is, so let us assume that is my X is a compact, or compact, compact 4-dimensional or n-dimensional manifold with boundary. Then we split the boundary of X into plus part and the minus part, and take the minus with minus. Then handle decomposition of X relative to the boundary and exactly to the minus part of the boundary is a manifold equipped with a filtration. So it starts with minus boundary times an interval, and this is like 0 part of the filtration. Then this sits inside of the first and so on, and somewhere you have X k minus 1 sitting inside of xk, and this is already your whole manifold X. And you require that you pass from xi, so from xi you go to xi plus 1 by attaching finitely many n-dimensional I handles. And such an X equipped with this filtration is called n-dimensional K handle body. So for example, the handle body which we have seen already today in the lecture. So let me start it here somewhere to give you examples. So we have seen this HG. This was our handle body when we were constructing the 3-cob. So what is this? So what is N and K in this case? So remember this HG, it was just basically 4-ball, a 3. Yeah. Okay. So I'm redrawing the picture. So this was something like this. So what is this?
1, 1.
1, 1.
Yeah.
No. But this is what is the dimension of this thing. So you start with an n-dimensional manifold. Yeah, n-dimensional manifold. So here I'm starting with a 3-ball. Yeah, 3D, 3-dimensional. This is a solid. This is 3-dimensional object. This handle body. Yeah, it's not just surface.
Right. So K is 2 and N is 1. No,
N is 3 and K is 1. So this is a 3-dimensional one handle body. Yeah, because 3-dimensional, this means the object will be 3-dimensional manifold. Yeah, this is 3-dimensional manifold. You agree? Yeah, it's not just about. So it's 3-dimensional. So this is just dimension of this coordinate or manifold we are working with, and these are one handles. Because these handles, it's always, so what are these handles? It's always I'm attaching D1 times D2 along the boundary. So the boundary is S0 times D2. This is the attaching regions. So I'm removing here from the boundary of my ball, I'm removing 2 disks, 2 D2s. So S0 is just 1, and so this is just, I'm removing these 2, and I'm replacing, so this is what goes out of the boundary, and it got replaced with D1 times boundary of this S1. Yeah, and this is S1 times an interval. This is the cylinder. So this is 3-dimensional one handle bodies. Okay.
What a 3-dimensional 2 handle body look like?
Okay, so 3-dimensional 2 handle body. Yeah. Okay, so what is a 3-dimensional 2 handle body? Good question. So now to construct this, I need to attach. So I mean, by the way, 2 handle bodies. This means it can also have 1 handles. So it can have this guy as well, but it may have, in addition, have also 2 handle. Yeah. So just let us consider the case of the 2 handle. So 3-dimensional 2 handles. So you can tell me from the definition, it's something which is D2 times D3 minus 2, which is D1. Yeah. So this means that So I'm taking, it's okay if I, instead of this cube, I'm drawing just a 3 sphere. So I'm 3 ball, even I'm taking 3 ball, yeah. And I need, so to attach it to handle along the boundary, where the boundary it's d2, which is S1 times D1. Yeah, this is just thickening of S1, and I need to embed it on the boundary of the 3 balls. So basically, so you give me a curve like this, and I'm removing its tubular neighborhood out of this ball, and I'm gluing a disc like this and disc like this. This is a 2 handle. So for example, what you can imagine is that if I'm sitting in this handle body, yeah, and now I'm drawing for you in this color the attaching curve of the 2 handle. For example, I would attach a 2 handle along this curve. So what would be the result? So this is the standard example of the handle cancellation. Yeah, so because I'm just gluing. So basically, what this handle creates, it creates this one non-trivial circle, and I'm immediately glue it with a disk. So I'm just gluing this with a disk, and this just kills this one, and the result will be hg minus 1. Yep. Good. Okay, so we understand the handle decompositions for 3-dimensional manifolds. Yeah, so we just need to go once higher. Okay, so should we do it for torus, or it's okay? Handle decomposition for torus. This is usually taught in the. Okay, so I assume you know. Yes, it's torus. You start with a disk, you glue 2 handles. So you have for torus, you have 1 0 handle, 2 1 handle, and 1 2 handle. Okay, and so example which we will consider later, it will be CP2. So this is already 4-dimensional manifold. Yeah, and here the handle decomposition is given by, you just have 1 handle in each even dimension. So you have 1 0 handle, 1 2 handle, and 1 4 handle. So this is CP2. Okay, I'll draw so I will just in a second I will give you a better way how to think this. Sorry?
There's a choice for the 2 handle.
Exactly. The so-called Kirby diagram, which will appear just unknot, one twisted unknot. Okay, so the main theorem. So why I'm bothering you with all this topology? It's because so there is a fact, and you can find so basically the whole. So my best reference for all this stuff, it's a book of Gompf and Stipschitz. So Stipschitz, I'm not sure I can write it. Okay, and so there you can find theorems that every smooth compact manifold pair in any dimension, inclusive the dimension 4, admit a handle decomposition, and this is just follows from the Morse theorem. Okay, so it always exists. This is already a good thing to know. And also, you know how to connect 2 different handle decomposition. Clearly, handle decomposition are not unique, as we have seen. For example, you can create 1 handle and immediately remove it so cancel it by the index higher handle. And then 2 handle decompositions are equivalent. They can be related by, and here you have a set of moves. So first of all, isotopies of attaching maps. So important is that this isotopies happens to be, so if I'm attaching K handle, then this isotopies happens in the xk minus 1. So I'm going, so you don't do this. So I'm going here. So these are isotopies of these attaching handles. They happens on the 1 level lower because I'm attaching to xi minus 1 my ai handle. Yeah. So there so for example so this 1 handles I can take this disk and move them around. So this would be isotopy of the attaching maps. Then there are more complicated moves, which are handle slides. So handle slides look like this. So I have here my sphere. I would like, so I attach two, say, two one handles. These are my two one handles, and I can take this attaching sphere and move this through the other handle. So the all way around, so it will be somewhere at some point here, and then it will go all the way around, so that at the end it looks like this. Okay, this is so I slide one handle around the other one handle, and this no, I'm trying through it. I'm sliding. So this is the intermediate step. It's just sitting on this. So this is my attaching map. So I'm just really going through the whole. So I'm going along this core all the way on the boundary, and I'm landing here in the neighborhood of this guy. This is handle slide. Okay, and this is this handle slides. It's I handle over I handles. So it's only slide of the handles with the same index. Okay, and then the last, this is what we already have observed there. It's the creation or removal of canceling pairs of I plus one handles. Okay, so this is exactly what I mentioned before. And now I would like to give you, so this doesn't move, but this moves. But this is this you don't need. So where is it? Okay. So this is not a good idea. Okay, this is not a good idea, and I have to clean this one. I just will give you a way how you can think about this handle decomposition in dimension 4. And so the usual the usual way to represent this handle decomposition in dimension 4 are so-called Kirby diagrams. So what is this Kirby diagram? So first of all, so we will work only with connected manifolds. So all our handle decomposition will start just with a zero handle, and zero handles is just dn. So you see H0n is just dn. So we start with the n-dimensional ball, or d4 in my case, and you would like to add, so you will construct your first manifold x1 by taking d4 and attaching to it some number of one handles, 4-dimensional one handles. So how it looks like? So if this is your four ball, then boundary of this guy is a 3-sphere. So boundary is a 3-sphere. On the 3-sphere, you remove two, so one handle H14, it's just D1 times D4, D3. So from S3, you remove two D3 from the boundary, and you connect them by handle. So this is attaching of one handles to D4, and then to construct a second level of filtration, X2, you need to take X1 and attach two handles to this guy. So assume I have, for example, here two. I attach first to one handles, and then how I attach two handles, it's exactly the same procedure as I described here in 3-dimensional case. What you need to specify is now for the two handles, this is D2 times D2, and you need to attach it along S1 times D2, which is a solid torus inside of S3. Yeah, and actually, it's enough to know how the core of this solid torus looks like. And so, for example, you can just draw here some attaching map of a two handle. So it's just some knot on the boundary. So in the S3. This will give you an attaching. So basically, it should be a frame knot because you need actually a tubular neighborhood of this guy. Yeah. So such a picture. So this one handles together with these knots. This will give you a four-dimensional two-handled bodies, and this is what we will consider in the next lecture. So it will be about four-dimensional two-handled bodies, and you preserve them in the following way. So for example, here you have one node, and perhaps you have another node which can be moved with this one, and go, for example, through this handle. Okay, then the Kirby diagram. It's just a diagram for these two nodes together with meridians of one handles, which are going above, which are standing like it's just going like this. And here also meridian, which is going, so meridian going like this, and putting a dot. So like if you forget about all in white, then this is a so-called Kirby diagram of a four-dimensional two-handled body. So basically, this is just a diagram which consists of together with unknots, and these unknots correspond to the belt spheres of the one handles, and they're dotted. Like so basically, you just split the components of your link. So three manifolds you usually just present by links. Yeah. Here you have like undotted component which stands for your two handles, and dotted components which stand for your one handles. So basically you just have a diagram where the components are dotted or unknotted. The undotted can be linked and knotted, and the dotted are just unknots. Just because these are all just the meridians of this. I just need to know whether this line goes through this one handles or does not. And if it goes through this one handle, then I indicate this by putting this one meridian of this one handle. So this is a way to encode this complicated four-dimensional handle decomposition into just a diagram we are used to work anyway in three-dimensional topology. Okay, so I think this is a good point to stop. And so tomorrow I will organize these diagrams into a category. I'll show that this category is equivalent to this four-dimensional two-handled bodies, and shows that they are generated by some algebra object.
Any questions?
So maybe this will come later, but so the special case of this, what you said is if you have a non-factorizable category and you positively modularize, then you would have a three-dimensional TFT and a four-dimensional nucleus. What is the relation between them? Is there somehow a boundary? Or
exactly, it's just a boundary. Exactly. So basically, this invariants which I'm speaking about, this four-dimensional, they will exist. Yeah, but it will see only the boundary. It will not exactly. So basically, on the level of this diagram, it's so you see already that this two handle, it's just exactly the surgery inside of S3. So attaching two handle inside of this so on the boundary, it's removed S1 times D2 and replace it by again S1 D2, but in the other way. So it's exactly the surgery on the boundary. And in this one handle, you can also so this is exactly why we denote them by these circles, because on the boundary, doing a surgery along this meridian is exactly the same as adding this one handle. So basically, the invariant will not see the difference between dotted and undotted component, and we actually all will just reduce to the boundary. So say for factorizable for four-dimensional topology, it's just not interesting.
Any other questions?
It will be more algebraic tomorrow. So sorry for the mess with the handles.
Let's thank Anna again for